Hi everyone, my name is Jianwen Xie from Baidu Research. Today, I'm going to present a tutorial on theory and application of energy-based generative models, together with Dr. Yingnian Wu from UCLA. In recent years, there has been growing interest in ConvNet parameterized energy-based models. Different from existing popular generative models, such as GAN and VAE, the energy-based model can unify the bottom-up representation and top-down generation into a single framework. The expressive power and advantage of the energy-based model have launched a bunch of research works, leading to the advance of theory, algorithm, and application of energy-based models. This tutorial will provide a comprehensive introduction of current energy-based modeling and learning methodologies, and aims to enable researchers to apply the energy-based learning principle in other contexts of computer vision. We divide the materials into three parts. In the first part, fundamentals, I will present background and basic knowledge of energy-based models. In the second part, advanced, Dr. Wu will present advanced energy-based methods and explain key ideas and equations. In the third part, applications, Dr. Wu and I will present applications of the current energy-based models. We shall start from the background of energy-based models. An image is a collection of numbers indicating the intensity values of the pixels, and it is a high-dimensional object. A population of images, such as images of cats, can be represented by a probability distribution, which is parameterized by a set of parameters that can be trained from the observed data. Such a probabilistic model is useful for supervised, unsupervised, and semi-supervised learning, as well as model-based reinforcement learning. Therefore, studying probabilistic models is a fundamental problem in computer vision and machine learning. The energy-based model that we will study in this tutorial is one type of probabilistic models. We will talk about Gibbs distribution in statistical physics. Energy-based model originates from the Gibbs distribution in statistical physics. In the Gibbs distribution, X is the state of a system. For example, a cup of water, gas. E of X is the energy of the system at state X. T is the temperature. As T goes to 0, P of X focuses on the global minima of the energy function of X. Z is the normalizing constant or partition function to make P of X a probability density. The partition function is ubiquitous in statistical physics or quantum physics. States of low energies have high probabilities. In this tutorial, we are going to present energy-based model. X can be an image, a video, or a text. The negative energy function divided by the temperature T will be parameterized by modern ConvNet, f of X, where theta denotes the parameters. F capture regularity, rules, organization, and constraint probabilistically. In conditional settings, Fx acts as soft object function, cost function, value function, or critic. It actually is a softmax probability. Here, it assigns score fx to each x, as if each x is a category. Next, we will talk about frame models. In the field of computer vision and pattern recognition, the frame model was proposed for texture modeling. The frame model is a Markov random field model, or an energy-based model whose energy function is the sum of translation invariant potential functions that are one-dimensional non-linear transformation of Gabor filter responses. It assumes a dictionary of Gabor filters is given, and only learns weights theta on top of the nonlinear transformation of filter responses. These are some synthesized texture patterns sampled from the learned frame model by Gibbs sampling. The grade model tries to learn the frame model by using Langevin sampling for texture synthesis. The Langevin Dynamics is a gradient-based MCMC method, which consists of a gradient ascent term and a diffusion term. Since the original frame model for texture is homogeneous, it cannot be used for object patterns. The inhomogeneous frame model is a non-stationary Markov random field model that reproduces the observed statistics of Gabor filter response at all the different locations, scales, and orientations. It used HMC for sampling. In the language of neural network, the energy function of the inhomogeneous frame models are a two-layer network, in which one convolutional layer, that is Gabor filter, is given, and one fully connective layer is learned. The deep frame model replaces the Gabor filters by VGG features and learn one fully connective layer. These are the generative examples by Langevin sampling from the learned deep frame model. Now we will present Generative ConvNet model, which is an energy-based model parameterized by modern neural network. Instead of using filters from pre-trained ConvNet, we can learn the filters from the observed data. The resulting model is the Generative ConvNet model. Such a model can be considered a recursive multi-layer generalization of the original frame model. Let X be an image. The Generative ConvNet model is a probability distribution defined on image domain. Q is a reference distribution, for example, a uniform or Gaussian white noise distribution. Z is the normalizing constant, which is intractable. The Fx is parameterized by a ConvNet structure that maps the input image to a scalar. Theta contains all parameters of the ConvNet. For the rest of the part 1 of this tutorial, I will use the Generative ConvNet as an example to present the elements of energy-based learning. In this section, we will study an important concept, which is KL divergence. Suppose we have two probability densities, P and Q. The KL divergence between P and Q is defined as the expectation of log P over Q under the distribution of P. The KL divergence usually appears in two scenarios. The first scenario is maximum likelihood learning. Given the training examples X that are assumed to be sampled from an unknown data distribution P data, we want to learn a model P of X parameterized by theta from the data by maximum likelihood. For a large number of training examples, maximizing the likelihood is equivalent to minimizing the KL divergence between the data distribution and the model. The expectation under the data distribution can be approximated by averaging over the training examples. The second scenario is variational approximation. Suppose there is a target distribution, P of target, which is known up to normalizing constant. For example, the P target is an energy-based model where negative energy function fx is known. Z is the intractable normalizing constant. Suppose we want to approximate the target distribution by a distribution Q phi, where phi is the learning parameters. We can find phi by minimizing the KL divergence between Q phi and P target. This time, we place Q phi on the left-hand side and P target on the right-hand side of the KL divergence. Because P target is accessible through fx, the above minimization doesn't require knowledge of log z. The behaviors of KL divergence in scenario 1 and 2 are different. In the MLE scenario, the learned model P theta tends to cover all the modes of the target, which is the P data. While in the scenario of variational approximation, the learned model Q phi tends to focus on some major modes of P target, while ignoring the minor modes. The reason is because the KL divergence in the second scenario is expectation with respect to Q phi. The figures displayed below demonstrate the difference between these two settings. Now we will talk about maximum likelihood estimation and analysis by synthesis algorithm. Maximum likelihood estimation is a commonly used method to train energy-based model. Suppose we observe training examples xi, which follow the unknown data distribution P data. The objective function of MLE learning is the average of the log probability density of the training examples. The gradient of the log likelihood involves an expectation term, which is analytically intractable. The expectation term comes from the derivative of the log z, where z is the intractable normalizing constant. We saw the derivation of the gradient of the log likelihood on the right-hand side. The expectation term is intractable because x is high-dimensional. Consider x is a 100 by 100 grayscale image, and each pixel can take a value from a region from 0 to 255. The image space is too big to do summation over x for computing the expectation according to the definition. Therefore, it has to be approximated by Markov chain Monte Carlo MCMC method, such as Langevin Dynamics or HMC. To be specific, we can sample x tilde from the model distribution and use the sample average to approximate the expectation. Now, we shall study Langevin Dynamics, which is a gradient-based MCMC method that is important and useful to compute the gradient of the log likelihood. For high-dimensional data x, sampling from the distribution P of x, which is in the form of energy-based model, requires MCMC, such as Langevin Dynamics. The Langevin Dynamics is a stochastic gradient ascent algorithm that finds data x to maximize the function f. Larger f corresponds to larger probability density. Delta t is the step size, and ET is the Gaussian noise term for randomness. As the step size goes to 0 and the number of steps goes to infinity, the distribution of x will converge to the target distribution P of X. There are different implementations of the Langevin sampling. First, for the persistent chain, we run finite step MCMC from the synthesized examples generated from the previous apple. Secondly, the contracted divergence runs a finite steps MCMC from the observed examples. Third, if we run finite step MCMC from Gaussian white noise, this will lead to a non-persistent short-run MCMC. This is a full description of the MCMC-based MLE algorithm for energy-based generative model. At each iteration, we first sample synthesized examples from the learned distribution by MCMC, and then use the training data and the synthesized data to compute the gradient of the log likelihood, such that the model parameters can be updated by gradient-based learning algorithm. The learning algorithm tries to match the synthesized example to the data in terms of some statistics. Such a learning and sampling algorithm is called analysis by synthesis algorithm. We are going to talk about adversarial self-critic interpretation. Here, I want to show you the adversarial interpretation of the energy-based learning. The update of parameters theta is based on the gradient of the log likelihood, which is the difference between the observed statistics and the synthesized statistics. If we take out the gradient sign of the summation operator and define a value function v, which is a function of the synthesized examples x tilde and the learning parameters theta, the gradient of the value function is equal to the gradient of the log likelihood. We can easily find that the learning and sampling algorithm actually play a minimax game. In the learning step, the algorithm finds theta to maximize the v, and in the sampling step, the algorithm finds x tilde to maximize the score function f, thus minimizing the value function v. Please also see part 2 of the tutorial for adversarial contractive divergence for EBM. The analysis by synthesis learning algorithm is a mode-seeking and mode-shifting process. Here is an illustration. The red curves and blue curves represent the negative energy landscapes of the true model and the learned model, respectively. The red crosses indicate observed data, and the blue circles indicate the synthesis data. Figure 1 is the mode searching by Langevin Dynamics, which finds high-score modes in the landscape of the model, and placing the synthesized examples around the found modes. After that, the algorithm shifts the high-score modes toward the observed examples, which is shown in Figure 2. Figure 3 is the mode tracing, which researches the high-score modes in the updated landscape of the model. Figure 4 is the mode matching, where the modes in the learned landscape eventually match the ones in the data distribution after a few iterations of mode searching and shifting. Now, we are going to talk about short-run MCMC for EBMs. Given an energy-based model P of X, E is the intractable normalizing constant. Fx is the negative energy. Theta are the parameters. The maximum likelihood learning of the energy-based model P of X requires the MCMC sampling, such as Langevin Dynamics. to approximate the gradient of log likelihood. The Langevin Dynamics is an iterative algorithm where each step consists of a gradient ascent that maximizes the function f and the noise term serving as Brownian motion. The model P of x can be highly modeled, and the gradient-based MCMC may get trapped in local modes, so that different Markov chains initialized from different starting points do not mix. We now consider the learning algorithm based on short-run MCMC. To use a short-run MCMC, we initialize the Langevin dynamics from a fixed initial probability, P0, and run a fixed number of k-steps. The resulting marginal distribution of sample x after running k-steps of MCMC starting from P0 is denoted by Q of x. Since the short-run MCMC is non-convergent, so Q of x is not equivalent to the target distribution P of x, and x is highly dependent to its initialization. Therefore, the k-step short-run MCMC can be considered as a latent variable model or a generator with initialization z as latent variables. Here we use M to be the transition kernel of k-steps of MCMC toward the target distribution. The short-run MCMC can be written as x equal to M of z, where M is nonlinear mapping and z is latent variables following the distribution P0. This figure shows some generative examples by short-run MCMC. Training the parameters of the energy-based model with the non-convergent short-run MCMC is no longer a maximum likelihood estimator, but a moment matching estimator that solves the following estimating equation, which is the perturbation of the MLE estimating equation, where we just replace the model P by the short-run distribution Q of x. In part 2, we will present methods to improve sampling and reduce bias due to perturbation of MLE, or to avoid sampling. Now, I want to show you how to understand the learning behavior of the short-run MCMC. Let's consider a simple model where we only learn top layer weight parameters, theta. The blue curve illustrates the model distributions corresponding to different values of parameters. The black curve illustrates all the distributions that match the data distribution in terms of the expectation of hx. The hx is a feature vector of x. The ideal MLE solution, which is the green dot, is the intersection between the blue curve and the black curve. The red dotted line shows the MCMC starts from P0 and runs toward P with theta hat MME. MME means moment matching estimator. But the MCMC stops after k steps, reaching Q with theta hat MME, which is the learned short-run MCMC generator. Even if the learned P of theta may be biased from MLE, the resulting short-run MCMC is considered a valid model in that it matches the data distribution in terms of expectation of hx. As we mentioned before, the short-run MCMC can be considered a latent variable model or generator. Therefore, it can be used for reconstruction or interpretation. In the top figure, we show that with the short-run MCMC generator, we can find latent variable z for each images. and perform linear interpolation on the latent space. The transition in the top figure displays the sequence of generation with interpolated Z. In the bottom figure, we saw that the short-run MCMC generator can perform reconstruction by finding Z to minimize the reconstruction error. Both of these experiments validate the learned short-run MCMC is indeed a latent variable model. Now, we will talk about equivalence between EBMs and discriminative models. In this section, we will show you the equivalence between the energy-based model and the discriminative model. We will first introduce the discriminative model. Let X be an image and Y be a label of X. Suppose they are C categories. The probabilistic model P of Y given X for classification is in the form of softmax classified, where F is a deep net and theta denotes all parameters of the network. For different category C, the network F outputs a different value. Therefore, we use the subscript C to index the F. Different C can share a common body of the network F and only have a different head layer in F. This softmax model can be rewritten to an energy-based form with Z representing a normalizing constant. Since the space of C is small, the computation of Z is tractable. We can learn the discriminative model by maximum likelihood. The gradient of the log likelihood with respect to the parameter theta involves an expectation terms due to the derivative of log Z. The maximum likelihood minimizes the KO divergence between the conditional distribution of data and the model. The calculations are analogous to the calculations for the energy-based generative model. The difference is that for the discriminative model, the normalizing constant Z and the expectation are summations over Y, where Y belongs to a finite set of categories. While for the energy-based generative model, the normalizing constant Z and the expectation are integral over X, where X belongs to a high-dimensional space. Therefore, the expectation in the energy-based generative model cannot be calculated in a closed form and has to be approximated by MCMC sampling, such as Langevin Dynamics. A special case is binary classification. They can take either 0 and 1, and the model is a nonlinear logistic regression model. Here I want to show the EBM and discriminative model are equivalent to each other. A more general version of the energy-based model is of the form of exponential tilting of a reference distribution. Let X be the data. Qx is a reference distribution, such as uniform distribution or Gaussian white noise distribution. The original form of the energy-based model corresponds to Qx being a uniform distribution. If Q is a Gaussian distribution, then the energy function is negative f plus x squared divided by 2. Even though Q is usually taken to be a simple known distribution, Qx can also be a model. We call it a based model or a backbone model. And P of x can be considered a collection of Q of x. And the Fx is the collection term. We may call Px the energy-based collection of the based model Qx. We want to show that this exponential tilting leads to a discriminative model. We can treat the P of x as positive distribution and Q of x the negative distribution. Let y be a binary variable which can take value from 0 and 1, and y is label of the distributions. We also assume a prior probability of y equal to 1 is rho, so that the prior probability of y equal to 0 is 1 minus rho. P of x given y equals to 1 is our distribution P of x, and P of x given y equal to 0 is the reference distribution Q. According to Bayes' rule, the model can lead to a discriminative model, which is a logistic regression. More generally, suppose we have C categories. Each category corresponds to one energy-based distribution. F with subscript C are C networks that may share the same body but with different heads. Suppose the prior probability of category C is rho C. Then we can derive a conventional softmax classifier from the energy-based models. Conversely, if P of y given x is of the form of softmax classifier, then P of x for a specific category will be of the form of exponential tilting. Therefore, the discriminative model and the EBM are equivalent to each other.
Welcome back. We now begin the second part of this tutorial. First, we shall present strategies for efficient learning and sampling of the energy-based models. The first method is a multi-stage coarse-to-fine expanding and sampling method. Suppose we want to learn an energy-based model. So in the training stage, we incrementally grow the energy-based model from a low resolution or a coarse model to a high resolution or a fine model by gradually adding new layers to the energy function. So each time we add new layer. And then in the testing stage, we just keep the learned models and we use short-run MCMC, for example, Langevin Dynamics, to sample the images at the highest resolution eventually. And this method proved to be very effective for generating very realistic images. This slide shows some result. So the figure on the left shows the MCMC generative sequence after learning the model on slip A data, where we use 50 Langevin steps to generate the images. And the figure on the right shows the generated examples after learning the model on the slip A high-quality data at 500 by 500 resolution. So you can see that the generated images are very realistic. Next, we present a related method. This method is a multi-grid modeling and sampling method where we learn multiple models at multiple resolutions or multiple grids. And when we sample a model at a higher resolution, we always initialize the finite step MCMC sampling from images sampled from the models learned at lower resolutions. And of course, the lowest resolution is 1 by 1, where the model is simply the histogram. So the sampling process starts from this 1 by 1, the lowest resolution, and then we keep using finite step MCMC to sample the current resolution, initializing from the previous resolution. So this way, we generate images at multiple resolutions and multiple grids. And then we can learn the models at multiple grids. So this shows you some examples where we generate face images at bigger and bigger resolution. This slide shows some examples. So the figure on the left shows some images generated from the learned model after learning from Cipher dataset. And the figure on the right shows some examples of imprinting, where the first image is the original image, The second image is a masked image where some of the pixels are masked so that they are not observable. And the third image is a recovered image. We still use the same sampling method to generate or to recover the image, except that in the sampling process, we always fix the observed pixels at their original observed values. And you can see that the MC sampling at multiple grids according to multiple models can enable us to recover the masked pixels. And the last example is a numerical example where we show that this method can be used for semi-supervised learning. So as we discussed in the first part, the energy-based model can be considered a generative classifier. However, we can learn the bottom-up network from unlabeled data. And after learning this model, this energy function, we can then use the top few layers as features. And then when we want to learn from the labeled data, we only need to grow a small network on top of those layers. So this enables us to learn from small amount of labeled data after pre-training on very big unlabeled data. So this method proved to be very effective for semi-supervised learning. We now introduce the third method. The third method is a diffusion-based modeling and sampling method. It is actually similar to the previous two methods, except that instead of creating images at multiple resolutions or multiple grids, we actually keep adding noises, the Gaussian noises, to the image in a diffusion process. So by adding more and more noise, we eventually arrive at a white noise image. So at time step t, the xt is obtained by adding Gaussian noise of variance sigma squared to the image at the time step t-1. So this process, if you repeat it, it is a diffusion process, eventually leads you to a white noise image. So this is this q xt given xt-1. So this is a very simple diffusion process. And what we want is to learn the energy-based model for the images at all those noise levels corresponding to all those time steps. So the model is parameterized by a single network, which is a function of both x and t. So here we can use a certain vector embedding of t so that all those models are parameterized by a single network. Of course, it's still very difficult to learn those energy-based models marginally. However, we can learn, or we can first translate this energy-based model into a conditional version. So that is, if we consider the conditional distribution of xt-1 given xt, so that is, given xt, we want to recover xt-1, where xt is a noisy version of xt-1. And this distribution can be considered as a prior distribution of xt-1. And then we add this data likelihood, right? So which is a least square term, so that the marginal distribution continues to be an energy-based model with this energy function. And you can see that because of the regularization of this term, so given xt, this term requires that xt-1 to be close to xt if sigma square is small. So therefore, even though the original energy function may be highly multimodal, with this regularization, it is actually quite close to unimodal around xt, and the sampling become very easy. So it is just sampling from a conditional distribution which is close to unimodal. And this is actually a matter for denoising, or you can think of this as recalling xt-1, where we gave xt as a hint so that it is much easier to sample from than sampling from the marginal distribution. Okay. Okay, so after sampling images from this conditional distribution, where this xt is given as a noisy version of x0, you just add a certain amount of noise to the original clean image. And then you can learn the models at multiple noise levels or multiple time steps by using the same method, analysis by synthesis method. And then you learn this F network. So you learn the marginal models at all the noise levels. And then in the generation process, after learning these models, you can start from this white noise image. And then you repeatedly sampling from this conditional distribution. Okay, so sample from those conditional distribution. Eventually, you will generate the clean image. So this is a reverse for this diffusion process, aided by the energy-based model. And in this process, we learn energy-based models at multiple noise levels. So it is very similar to multi-grid method, except that we don't learn at multiple grids or multiple resolutions, but we learn the model at multiple noise levels. So we call this method the diffusion recovery likelihood method. And these figures show some examples generated by the learned models. And you can see that they are actually very realistic at high resolution. And in terms of the FID score and the inception score, so this method achieves the best synthesis performance or synthesis quality among all the energy-based models. And here are some examples of imprinting, where the first row shows the masked images and the second row shows the recovered images, and they are quite realistic. We now move to the second part, where we incorporate a generator network. So we treat the generator model as an approximate sampler for the energy-based model. So a generator model is actually a top-down model, where we always consider the observed example, for example, image at the bottom. And then this image X is generated by a hidden vector Z, a low-dimensional hidden vector Z, through a top-down network. So Z at the top and X at the bottom, and Z generate X through this top-down network G of theta. Okay, so this is G is a top-down mapping. So this is the structure for the generator model. And if we consider the energy-based model, the energy-based model is parameterized by a bottom-up mapping or a bottom-up network, where again, the image or the example X is at the bottom, and then we use a bottom-up network to compute the energy function, the negative F theta of X. Okay, so this is the form for the energy-based model. So for the energy-based model, you only need to specify a scalar function. So this F is a scalar function. Okay, but this G is a vector value function. It needs to produce this high-dimensional X. So therefore, it is much easier to specify or to learn this scalar function. And we can think of this F as an objective function, or the negative F to be the cos function, and F can also be considered as a value function. And you can think of this as a critic or teacher, as I will show you later. So as I mentioned, this energy function is easy to specify and easy to learn. However, we know that it is very difficult to sample fair samples, examples from the energy-based model. And because we specify this F directly, so it is a explicit approximation to the data density. And oftentimes, it gives us a very strong approximation to the data density. And back to the generator model, it is specified by a top-down network. And as I mentioned, it is a vector-valued function. And you can think of this as an approximate sampler of the energy-based model, which is how we use the generator network. And in the language of reinforcement learning, you can even call this as a policy network as compared to the energy function, which can be related to the value network. And you can also call it as an actor or a student. And the advantage of this generative model is that you can generate the synthesized images directly by this ancestral sampling. You just sample Z from its very simple prior distribution and then feed Z to this top-down network to generate your X. However, this model only gave you a implicit marginal density. The marginal density involves intractable integral. And this model follows the so-called manifold principle, which assumes that the data lie very close to a low-dimensional manifold, maybe plus some Gaussian additive Gaussian white noise. But this model may not be a very strong approximation to the data density, may not approximate the density as well as the energy-based model. And these two diagrams illustrate the ideas of learning the two models. For the energy-based model, in our past work, we call this a descriptor in comparison to this generator. So we just use EBM, but this is where we get D1 and D2. So you have inner loop, you use the Langevin dynamics to generate synthesis examples. And then by comparing the synthesis examples to the observed examples, you update the model parameters so that eventually they match in terms of statistical properties. And in learning the generative model, you also need an inner loop to infer the latent factors in this hidden vector Z. And you can use Langevin dynamics for posterior sampling. And after you infer this hidden Z, you can then learn this top-down network as a matter of least square regression. That is, you want to let G to generate or to be close to the observed examples given or by transforming this inferred hidden vector Z. More specifically, I guess most of you are already very familiar with the form of the generative model. So we have this latent vector Z follow a uniform distribution or a normal isotropic normal distribution, Gaussian distribution with mean 0 and identity variance cross matrix. So that is all the elements of Z are just IID standard normal random variables. And then X is generated by G of theta of Z, which is a top-down mapping, and plus additive Gaussian white noise. Okay, and as I mentioned, this model actually follows this manifold principle where the high-dimensional data is generated by a low-dimensional representation. And this Z can also be considered as an embedding of this high-dimensional X. So we embed this observed X into a low-dimensional Euclidean space where we can do simple linear interpolation or some simple arithmetic in this latent space. And then after that, this can generate very interesting properties, nonlinear interpolation in the high-dimensional data space. This slide shows some important quantities. For example, this generative model actually defines a conditional distribution of X given Z, which is just a normal distribution with mean G theta of Z, and with a very simple variance cross matrix, sigma square identity. And often we just assume sigma square to be a tuning parameter. And the theta parameterizes the top-down network. And then given the prior and the conditional, we can get this joint. The joint distribution of X and latent Z is just factorized as a prior for Z times the conditional of X given Z. And in the more detailed form, it is like this form. So this comes from this term, the least square term, right? And this is like the prior distribution. We assume it follows a normal prior distribution. And then the marginal distribution can be obtained by integration of this joint distribution, where we need to integrate out this latent Z. So that's why this marginal distribution is in general implicit and intractable. So this is very much unlike the energy-based model, where we have a explicit unnormalized density function. But here, the marginal density actually involves this intractable integral. And then given x, we can infer z based on the posterior distribution, which is the joint divided by marginal, and which is also intractable because the marginal distribution is intractable. Okay, now let us go over some technical details for maximum likelihood learning for the generative model. So first, we write down the log likelihood for a set of observations, xi, where I goes from 1 to n. We have n observations. And then the log likelihood is just average for the log likelihood for each observation. But here, this is a marginal distribution because we only observe xi. We don't observe the underlying zi. So we have to use the marginal distribution for the log likelihood function. And then for each generic x, then the derivative of log p theta x, this marginal density, will be just 1 over this p theta x according to the chain rule, and then multiply by the derivative of this density, the marginal density, which is the integral for the joint density, where we integrate out the latent z. And then we can move this derivative inside. And then we use a very commonly used trick, which also underlies the reinforced algorithm for policy gradient. That is, the derivative for the density can be written as the derivative of the gradient for the log density multiplied by the density itself. Okay, and sometimes we also call this as the score, the gradient of the log density as a score function. And then we can move this p theta x, this marginal, inside because this is integral for z. And then we get this joint divided by the marginal, which is the conditional distribution of z given x, which is also the posterior distribution of z given x, which serve as the basis for us to infer z based on x. And then we continue to have this score function, the derivative of the log density. Okay, and then you can write this as expectation for this score function with respect to the posterior distribution. And then the expectation can be approximated by Markov-Chain Monte Carlo. So after deriving the gradient for the log likelihood, we can then use a gradient ascent algorithm for learning this data. And you can see that when you compute this gradient, first you need to draw samples from this posterior distribution. That is, inferring z given this x. And this can be accomplished by, again, Langevin Dynamics, where you have this gradient ascent step. So that is, you compute the gradient of this log posterior with respect to z, and then you add this Brownian motion or a diffusion term. Okay, so then after a number of steps, you draw samples from this posterior distribution. So the gradient for this log posterior with respect to z is actually the same as a gradient for this log of the joint density with respect to z, because they only differ by this log of p theta x, which has nothing to do with z. Okay, so this is a form for the joint density, the log of the joint density. Okay, so that is, you compute the gradient of the log joint density with respect to z in the Langevin sampling for inferring z. After you infer z, then you can just plug in the infer z and then compute the gradient of this log joint density with respect to theta for learning. So that's how you update the parameters. Okay, and therefore you can think of this algorithm, the learning algorithm, as alternating back propagation algorithm. So you compute the gradient for this function with respect to z in this inner loop for sampling z, and then you compute the gradient for this joint density with respect to theta when you want to update the parameter. Okay, so the inner loop involve this Langevin sampling, which is affordable, but still it can be time-consuming. So with the above preparation, we are now ready to present the cooperative learning method so that we can learn both the generator and the energy-based model in a cooperative way. So the generator model, we denote this as a P of theta x, where we use theta to denote the parameters for this top-down mapping. Okay, and it is a implicit integral, right? So the marginal density is the integral of the joint density, so that it is implicit. And we denote our energy-based model this time by pi of alpha, because we already use P of theta for the generator model, the top-down generator model. So the bottom-up energy-based model, we now use the notation pi of alpha. So alpha collects all the parameters of this bottom-up network that defines the energy function f of alpha x. Okay, so this is our current negative energy function. And the z of alpha, again, is a normalizing constant. So we want to learn this generator model p theta and the EBM pi alpha in a cooperative way so that they help each other. So both can be considered as an approximation to the data density p data. So here we use p data to denote the data density, and we observe samples from the p data. So this slide presents the basic idea of cooperative learning, and we do this with a so-called MCMC teaching method. Again, we have a top-down generator model p theta, and then we have bottom-up energy-based model pi of alpha. Okay, so we learn the two models cooperatively in the following sense. So first, we generate zi hat from the prior distribution of the generated model, just Gaussian by noise, right? This is a noise vector. And then we use the current theta and g of theta to transform this latent vector to a synthesized image. Okay, so this is the image generated by the generated model. And then we treat the generated model as an approximate sampler of the EBM. So therefore, we run a finite number of Langevin dynamics towards this EBM pi alpha under the current parameter. So you can think of this xi tutor as a revision of this xi hat generated by the generator. So that is, the generator is like a student, and EBM is like a teacher. So a student writes the initial draft of the paper, and then the teacher then revises the paper to get to this xi tutor. So this is considered as the synthesis example from the energy-based model. And then using the synthesis examples, we can then compare them with observed examples to update the parameter alpha for the EBM, right? But then how do we update this generated model? Well, you can see that this xi hat is the original draft generated by the generated model. And then it is corrected or refined by the EBM to xi tilde. So originally, this zi hat, the generated latent code or the noise vector, reconstruct xi hat, right? Now we update our parameter from theta t to theta t plus 1 so that this zi hat now reconstruct this xi tilde, the revised example. So this way, we actually distill this Langevin dynamics, this finite step Langevin dynamics into the generator model. So the generator model learns from the revision made by the EBM. So what's the advantage of this learning method? The reason is that this zi hat is known. So in this generation scheme, so for this xi hat and xi tilde, we actually know zi hat. Okay, so we just let the known zi hat to reconstruct xi tilde instead of xi hat, so that we can refine or improve the generator model. So this way, we don't need the Langevin dynamics to infer this latent Zi, because we know this Zi. Of course, after you update this xi, the underlying Zi may also change. So if you want, you can also run a Langevin dynamics to further refine Zi to Zi tilde. Okay, so this way, then you can learn this theta so that this Zi tilde reconstruct this xi tilde. So this is a more rigorous scheme for this cooperative learning. So what we call MCMC teaching is that we use this short-run MCMC for refinement to teach the generator network. So that is the EBM as a teacher refines the initial draft of the generator, and then the generator learns from the refinement by updating its parameter to absorb the refinement. So you can think of from xi hat to xi tilde, this refinement process, as a tempo difference process, because you run some steps of Langevin dynamics according to the EBM, right? So you can think of this also as a tempo difference learning method. Okay, and as I mentioned, this Zi hat can also be inferred more rigorously, but then this Langevin dynamics can be initialized from Zi hat, and Zi tilde will only be a very small perturbation for this Zi hat. Okay, so this diagram illustrates the basic idea of cooperative learning by MCMC teaching. So that is the generator generate the initial draft from the generated noise vector. Okay, and then the EBM then refine it to the revised synthesis examples. And then you compare the synthesis examples with the observed examples to update the EBM, just like how we learned the EBM before. And then here, you then use the generated latent vector and the refined example to update the generator, so that the generator should absorb the refinement made by the EBM as a teacher. Okay, so this is a basic idea of cooperative learning, and we call this as a ConvNet algorithm. The theoretical underpinning of this learning algorithm is as follows. So the learning of the EBM actually follow a modified contrastive divergence. We know that in contrastive divergence, you run a finite step of MCMC from observed examples. But here, we run a finite step MCMC where we use this M to denote the transition kernel from the examples generated by the generator model instead of from the observed examples. So basically, we use the generator model to jumpstart the MCMC, or we use the generator model to amortize the MCMC sampling for the EBM. Okay, and then the learning of the EBM follow the gradient of this contrastive divergence. So the first Kell divergence defines the MLE, and we have a second Kell divergence in order to cancel this log Z term. Okay, and the learning of generator is by the so-called MCMC teaching. So that is let P theta T be the marginal distribution of the generator model at current theta T, and then you run a few steps of MCMC towards the EBM, the current EBM. And after a few steps, you get to this distribution. And actually what you do is to project this distribution onto the manifold for the generator model. Okay, so you updated theta T plus 1, which is obtained by minimizing this Kell divergence. So as if the training data becomes a refinement for the generated data. So the learning by MCMC teaching is that the inference of the latent Z become very easy, because you know what latent noise Z that you use, the noise vector Z that you use to generate the initial draft. Okay, so therefore the advantage of this cooperative learning is that the generator jumpstarts the sampling, MCMC sampling of the EBM. And the EBM actually help to refine or to improve the generator model. So that's the basic scheme of this cooperative learning. This slide shows some results. So here are some texture images generated by the learned model. Actually, we learn two models simultaneously. And here are some scene images generated by the learned models. And also this interpolation result by the learned generator. And also we can use the model for impending applications. We can further improve cooperative learning scheme by a variational version of MCMC teaching, where we learn a inference model very much like a VE. I will skip over the details except showing you some synthesis results. But I would like to conclude the presentation of cooperative learning with a comparison with GAN. So in GAN, you learn a generator. However, in cooperative learning, you learn both the generator and energy-based model so that there is a refinement process according to the learned energy-based model. So this often leads to visible improvement of the examples produced by the generator model. So this actual refinement process proved to be quite important. And this is the key difference between our method and the GAN method. We now move on to the next method that completely avoids MCMC. We call this method Divergence Triangle, where we don't use any MCMC. So it is a framework that integrates variational and adversarial learning. So the generator involves the variational autoencoder, where the encoder serves as an approximate inference model. And the energy-based model is learned by the so-called adversarial contrastive divergence. And then if we put these two together, we actually arrive a very elegant form of a divergence triangle that involves three Kullback-Leibler divergences between three joint distributions. First, we recast the variational autoencoder for the generator learning from the perspective of Kullback-Leibler divergence. So we treat this as a so-called divergence perturbation. So first, a little bit notation. So again, we have Pz as a prior for the noise vector, and then P theta x given z defined by the top-down generator network. And then this gave us the joint distribution of observed x and the latent code z. Okay, and we call the joint distribution as P. So it is parameterized by theta, which are the parameters in the top-down mapping, top-down network. Okay, and in the variational autoencoder, we also learn a inference model, which is often written as Q of phi of z given x. So this is in an explicit form, often assumed to be a Gaussian distribution. And this is approximation to the true posterior distribution of P of theta z given x, right? And then we also have the data density P data. So the expectation with respect to P data can always be approximated by average over observed examples, okay? And we have this P data of x, and then we pair it with this inference model Q phi z given x. So this gives us another joint distribution of x and z. In fact, x can be considered as observed data and z as missing data. So this inference model is like imputing the missing data so that we have this Q parameterized by phi of the joint distribution of x and z. Okay, so this is another joint distribution. So in fact, if we look at VE, it can be considered as a joint minimization between this Q of phi and P of theta. So this is the data distribution, and this is the model distribution. However, this time, this is distribution of the so-called complete data, where X is observed and Z is missing or hidden. Okay, and this joint chiral divergence is actually tractable. And this is actually a perturbation of the first chiral divergence from the data distribution, the marginal distribution of the data, and the marginal distribution of X according to the model. Okay, again, this is a data distribution and this is a model distribution, but both are marginal distributions, and this one is intractable. Okay, so therefore, we add the chiral divergence between this conditional distribution, the two conditional distributions, so that we make them into the chiral divergence for the joint distributions. So that's what we call divergence perturbation. So this first divergence underlies maximum likelihood, okay, and it is intractable because the marginal density is implicit. But with this perturbation of this term, which is a very important term in variational inference, we change this chiral divergence between the marginals into the chiral divergence between the joints, okay, so that this becomes tractable. And then you can think of this VE as an alternating projection. So you have a Q family where each point is corresponding to a value of phi, right? And you also have this P family. So you do this alternating projection until convergence. So this is how we understand variational autoencoder from this divergence perturbation perspective. We now try to understand the joint training for energy-based model and the generative model, again, from the divergence perturbation perspective. And in fact, we can focus on this formula. So P data is a data distribution, and the pi alpha, again, is the density of energy-based model with the parameter alpha, because we use theta as a parameter for the generative model, P theta. Okay, so now if you look at this, this expression, so the first chiral divergence is a chiral divergence between data density and the density for EBM. So this is actually underlies the MLE, maximum likelihood learning for energy-based model. However, the log Z term, we know that involve intractable expectations that can be approximated by MCMC. Suppose we don't want to use MCMC, then we can use a generative model as a approximate sampler. And then we define the following adversarial learning, where again we minimize this chiral divergence over alpha. So the minimizing the first chiral divergence leads us to maximum likelihood. And then we subtract the second chiral divergence, which serves as a perturbation, and this time a negative perturbation by the second chiral divergence. And this negative sign actually underlies the adversarial learning. So this objective function actually can be more elegant than the original GAN objective. And in fact, it is closely related to Weierstrass GAN and also inverse reinforcement learning. So let's try to parse this formula more carefully. So you can see that actually this defines a chasing game in the sense that, so here, if we want to maximize this value function over theta, so this first part does not involve theta, right? So that means we need to minimize the second Kullback-Leibler divergence so that we want the perturbation to be as small as possible, or we want this P theta, the generator, to be as close to the energy-based model as possible. Okay, so that's the maximization part. And for the minimization, actually, this is a perturbation for this chiral divergence underlies maximum likelihood learning of energy-based model. Okay, and the learning gradient for alpha actually is just like this, as if we sample the synthesis images from this generator instead of from the current energy-based model. So therefore, you can see that here the generator chases this energy-based model, but this energy-based model try to get close to this data density as compared to the generator density. So it is like a chasing. So this p theta, this generator chases the EBM, and the EBM actually runs towards the data density and runs away from the density of the generator. So that is this pi of alpha serve as a critic. It criticizes this p theta, the generator, against the data. Okay, so this is adversarial interpretation, which has a very clear chasing interpretation. Okay, probably it is more clear than the original GAN objective function, especially in this very simple form for contrastive divergence. Again, this is in the form of contrastive divergence, except that the synthesis examples are generated by this generator network. Okay, now we are ready to put adversarial learning and variational learning together by this divergence triangle. So it involves three joint distributions on Z and X. The first one is a Q distribution, which is a P data X times this inference model. The other is a P distribution, which is a generator model, the joint distribution of the generator model. The third one is the pi distribution, which is the energy-based model times this inference model. Actually, you can also replace this by a so-called latent energy-based model that define a density on both Z and X. Okay. Now we have these three joint densities on Z and X, and then we can define the following divergence triangle, which is in this form, and then we either max or min over those three parameters. So this enables us to learn all these models simultaneously without MCMC. In particular, there's a VE element where this P and Q, they run towards each other. And then there's the adversarial contrastive divergence element where this P runs towards pi. You see, P chases pi, but the pi runs towards Q and runs away from this P. That's why we use this right arrow. So pi runs away from P, but the P chases pi towards this Q, the data distribution. So in this way, we can learn the energy-based model without MCMC because we use the generator as a approximate sampler. And also we can learn VE or generator model with a better synthesis because now the learning of the generator model is actually regularized by the EBM as the target density. So that is, this P has to be close to this target density defined by this energy-based model. Okay, so this gave us a unification or at least an integration for adversarial learning and variational learning. This slide shows some image generation results and also interpolation results in high resolution by this divergence triangle. We are now ready to move to the next part, which again involves a generator model. However, instead of learning a generator model and energy-based model separately, we now learn an energy-based model in the latent space of a generator model. We call the resulting model as the latent space energy-based prior model. So again, we let X be the observed example, for example, an image, and Z the latent vector. And again, Z generate X through a generator network defined by parameter beta. And then P0Z is the original prior model, for example, Gaussian white noise model or uniform model. But this time, we also learn a small network in the space of Z So this F alpha Z parameterized by alpha is a neural network defined on Z. So because Z is a low dimensional, so it can be a very small network. Okay, and then we assume that the prior model for the latent Z follow a exponential tilting of the original non-informative prior model. Okay, and then Z still generate X through this G, the generator top-down mapping. Okay, so therefore, now the energy-based model is defined on Z, and it stands on a top-down generator. And in fact, the model P of alpha, the prior model, is exponential tilting of the original non-informative prior. So this actually follows the so-called empirical Bayes principle, where we can also learn the prior distribution from the data empirically. And because this Z is low dimensional, so this F alpha that defines the energy-based model can be a very small network, and yet it can lead to significant improvement in the model over the original generator model. The model can also be applied to text modeling, where X is a sequence of tokens in a sentence. So we only need to change the generation model into a autoregressive model parameterized by a recurrent neural network. And then each token is generated conditioning on the previous tokens, and more importantly, the latent vector Z. So Z is a thought vector about the whole sentence, and it controls the generation of the sentence at each time step for each token. So the latent space EBM is like a value function for planning the thought vector Z. And this thought vector Z enables the abstraction of the whole sentence. So this model can also be applied to other sequence data or time series data. We can continue to learn the model by maximum likelihood. So this is actually very similar to what we derived before. So the gradient of the log likelihood can be written as the expectation with respect to the posterior distribution of the gradient for the log joint density. And this time, the joint density can be decomposed as the prior and this conditional. Right, the prior is parameterized by alpha, and the conditional is parameterized by beta. Okay, so this gradient follow the same derivations as we did before. So the learning gradient for the EBM prior distribution or prior model is like this. So it is similar to the previous learning method for the data space energy-based model. So the only difference is that here you see the learning gradient. This part, so the expectation is not for the observed X, because now this network is defined for latent Z. So for each observed X, we need to infer Z from its posterior distribution. Okay, and then this is the derivative of log Z term. Actually, it's just the expectation under the prior model. So this is like a data part, and this is like the model part. We want to match the model to the data. However, here, the data is actually the posterior distribution of Z given the observed X. And in fact, after learning, we actually match this prior distribution with the aggregated posterior distribution, averaged over all the observed X. And the learning of the generator is still the same as before. It's just a reconstruction. So after we infer this Z, we can then learn G to reconstruct X from this Z. And this arrow in the yellow color denote the conditional distribution of Z given X, which is the posterior distribution. The model enables the matching between the prior model and the aggregated posterior distribution. Specifically, let P tilde XZ be the joint distribution obtained by multiplying P data X, the data distribution of X, which is the empirical distribution of observed data, multiplied by P theta Z given X, which is a posterior distribution according to the model. And then we can obtain the marginal distribution of z and p tilde by integrating out x, which means we compute the expectation of the posterior distribution over the observed data. So this is aggregated posterior. And then if we look at maximum likelihood learning, which is to minimize the Kullback-Leibler divergence between the data distribution and the distribution of x under the model by integrating out z. So we can decompose this KL divergence into two KL divergence. One is the KL divergence between the aggregated posterior distribution and the prior model. So based on this term, we can see that the model seeks to minimize this term in addition to another term that involve beta, so that at least from the first term, we see that the maximum likelihood learning seeks to match the prior model to the aggregated posterior distribution. So this helps us to solve the discrepancy between the prior and aggregated posterior in the traditional variational autoencoder model. The maximum likelihood learning requires sampling from both the prior distribution and the posterior distribution, and the sampling can be accomplished by the Langevin dynamics. We can initialize the Langevin dynamics from the P0 distribution, which is the non-informative reference prior distribution, and then we run a finite steps of Langevin iteration where this pi z can be either the prior distribution or the posterior distribution. Because z is low dimensional, sampling can be very efficient and the Markov chain mix well, and the short-run MCMC can be used for both inference from the posterior or synthesis from the prior distribution with, say, k equal to 20 steps for MCMC. So this is a learning and sampling algorithm. So you read in a mini batch, and then you do prior sampling from the prior distribution, and then you do posterior sampling from the posterior distribution, and then you learn the prior model by comparing the sample from the prior distribution and the samples from the posterior distribution, and then you learn the generation model by reconstruction. So the algorithm is very simple and also very efficient. And this type of model is actually quite powerful, and it has been applied to many different applications. For example, image generation, text generation, and molecule generation, either unconditional generation or conditional generation. And it can also be applied to trajectory prediction, where the energy function can be interpreted as a value function or cost function. And it can also be used for semi-supervised learning, where the concept of information bottleneck can be very naturally incorporated. So in part 3, you are going to see those applications. You can also annotate MCMC sampling from the prior distribution and the posterior distribution by learned approximate samplers or learned models. And again, you can do that within this divergence perturbation framework or divergence triangle framework. And again, the first divergence underlies the maximum likelihood learning, and then you perturb it positively by the second KL divergence, which is between an approximate encoder or inference model, like in VE, and this true posterior distribution. Okay, so if you add this term, you actually get variational autoencoder. And in fact, variational autoencoder can still apply to this latent space energy-based model. You only need to incorporate this energy function, negative energy function. So that is this error indicating the conditional distribution of z given x can be approximated by an inference model. And similarly, the sampling of the prior distribution can also be approximated by a model, for example, flow-based model, if you want. And then you can train both the original model and approximated samplers by this objective function in the form of divergence triangle. where this positive perturbation actually corresponds to the positive phase, where you sample Z from the posterior distribution given observed X. That's why it's called positive phase. And then the negative perturbation actually corresponds to the negative phase, where you sample Z from the prior distribution. Okay. And in fact, you can also use this objective function and this theoretical framework to justify the use of short-run MCMC as an approximate sampler. And in fact, usually you can simply amortize the posterior sampling because this actually need backpropagation through this top-down network. So it takes a little bit more time. For prior sampling, actually it is very simple because this F is a very small network in the latent space. So a persistent MCMC chain can be very efficiently implemented. So we don't actually need to amortize the prior sampling. We only need to amortize the posterior sampling by variational autoencoder, and VE can still be generalized to this type of model. Here are some synthesis results and FID score. And in this slide, I will show you the generation by this short-run MCMC and also the long-run MCMC. So here we plot the energy. And you can see that even for the long-run MCMC, it still keep changing. That means it is not stuck in the local mode. And in fact, the MCMC in latent space mix very well. So therefore, the latent space seems to be a very natural home for the energy-based model, so that you can capture the regularities, constraints, or rules, or objectives, or cost, or values in the latent space very conveniently. The model also works well for text generation and achieves very strong quantitative performance. So please see part 3 for more details. We now move to the last part, which emphasizes discriminative learning without MCMC. We start from this noise contrastive estimation of EBM. So again, we want to learn such a energy-based model. This time we use a P of theta to denote the energy-based model, just like our Euro notation. And you can also write this as an exponential form where C is a log of Z. And according to this NCE method, noise contrastive estimation method, theta can actually be learned in contrast against a noise distribution Q. So this Q of X is a very simple distribution so that we can write down the normalized density in closed form. Okay, and then following the idea that EBM can be considered as a generative classifier, so we turn the learning of EBM into a discriminative or classification task, where we maximize the following objective function. Okay, so this is expectation with respect to P data. So this can be approximated by averaging over observed training examples. And this Q, so expectation with respect to Q, can be approximated by averaging over the generated examples from the noise distribution QX. So why we can use this J of theta? Actually, this is just the log likelihood of logistic regression in supervised learning. So very similar to GAN. So we use Q of X to generate those faked examples. And then we learn P theta X to tell apart the faked examples and the real examples. So this is a logistic regression where we introduce the label y equals 1 if x is a training example and y equal to 0 if x is a generated example from the noise distribution. And then according to the Bayes rule, let's assume that the prior probabilities are the same. Then the conditional distribution of positive given x is this ratio, right? This ratio according to the Bayes rule. And therefore, the log likelihood for each observation xi will be log of this one for the positive examples and log of 1 minus its probability for the negative examples. So this is nothing but the log likelihood for the logistic regression. And so here again, Q of x is a normalized density function of the noise distribution, and the p theta is a normalized density of the energy-based model. So we assume that the data, the true data, real data can be approximated or approximately explained by this energy-based model. Okay, and this actually follow the discriminative perspective of energy-based model. Okay, and then how do we choose this noise distribution? Actually, we use the flow-based model. We don't need to get into the details of the flow-based model, except that it is a composition of a sequence of invertible transformations where the Jacobian can be explicitly computed. Okay, and therefore, this flow-based model gave us a explicit, normalized density function for the x. So that is z is the original noise, and then we use a sequence of transformations, and we let g of alpha to be the composition of the sequence of transformations, and then we get x. So z often assumed to be Gaussian white noise, and after this transformation, using the change of variable, we actually can obtain the density of x in a normalized version in a closed form. Okay, and we use this type of model as the noise model because it gave us a very good approximation to the data density. So if we compare energy-based model with flow-based model, the energy-based model has a free form. You can use whatever CNN or any network to parameterize the energy function, and it directly corresponds to a classifier. But the maximum likelihood learning can be very time-consuming because of MCMC sampling. Flow-based model gave us exact density in the normalized form, and it can generate examples by direct ancestral sampling, right? You sample Z as white noise and transform it into X. But unlike the generative model, so this transformation G of alpha is an invertible transformation. But because of the invertibility and also the explicit Jacobian, so those transformations are actually of a very contrived form. So you have to compose those very unnatural and carefully designed transformations. So it is not very flexible and not very expressive. So therefore, we can combine or train the two models jointly and using this objective function. Okay, and the choice of this Q, as I mentioned, is first it should be very simple and it has an analytically tractable normalized form, and we can easy to draw sample from, and hopefully it is close to the data distribution. So a flow-based model serves this purpose perfectly. And in fact, I'd like to emphasize that we can also replace the flow-based model by variational autoencoder, and it also satisfies analytical tractability in one approximately because there's a extra layer of approximation by this approximated inference model. But actually, again, we can use VE as our Q, the noise distribution. Okay. But here, let's focus on this flow contrastive estimation, where we use Q as our noise distribution, and then we continue to use the log likelihood of the logistic regression as our value function, and then we estimate or we learn theta, which is a parameter of the energy-based model, and alpha, which is a parameter of the flow-based model, jointly by this very similar to this GAN scheme, right? This is very much like a GAN, and later I will show you the difference. And by this min-max adversarial training, we actually can learn both the flow-based model and the energy-based model jointly. Okay, and for this energy-based model, actually it just follow noise contrastive estimation, where the noise distribution is this flow-based model. But the learning of the flow-based model actually is minimizing a so-called Jackson-Shannon divergence from this Q alpha to the P data, assuming that the energy-based model to be a very good surrogate for the data density. So basically, we let energy-based model to be a surrogate of the data density to further improve or refine the learning for this flow-based model. So that's the basic idea for the joint training. But if we compare this scheme to GAN, in GAN we learn a discriminator, and the discriminator is actually based on this likelihood ratio, this one. Okay. However, in the flow contrastive estimation, because we know this Q, the density of this Q alpha, so the Q alpha is in explicit normalized form, we can actually also learn this P theta explicitly, so that we learn this energy function explicitly instead of just learning a ratio as in GAN, okay? Because we know the density for this Q, okay? And you can think of this Q as an actor or a policy in the language of reinforcement learning, and the P as a critic or value. So this is essence for flow contrastive estimation. And it can be used for image synthesis. In fact, it leads to a better synthesis that improve upon a flow-based model, because you have a energy function to further regularize the flow-based model, and it generates better FID scores than the flow-based model. More importantly, this method can also be used for semi-supervised learning. So that is for the unlabeled data, you can train both the flow-based model and the energy-based model jointly, where the energy-based model is trained in a discriminative way, like a classifier. So that is EBM is like a generative classifier, but it is learned from unlabeled data. So therefore, this method gives us a probabilistic generative framework for this contrastive self-supervised learning, which is a very popular topic. However, if we use NCE, noise contrastive estimation framework, actually we get a very rigorous probabilistic generative modeling method, so that we can unify both generative modeling and discriminative learning in this way. So this is the importance. So when you train a energy-based model, you are not training a generative model, you are also training a classifier, or at least a pre-training for a classifier that can be used for downstream classification tasks. This example shows that this method indeed leads to very good performance on semi-supervised learning.
In part 3, we will cover the recent applications of the energy-based models. We will divide the applications into 3 groups according to the use of different types of energy-based frameworks. They include applications of energy-based models defined on data domain, applications of energy-based models jointly trained with a top-down generator, that is, cooperative learning framework, and applications of energy-based models defined on latent space. Now, we will first talk about the applications of energy-based generative models on image domain. This is the most popular application of the energy-based models. Learning energy-based generative models for image modeling and synthesis has been very successful. This figure shows some image generation results sampled from the energy-based models by using Langevin Dynamics sampling. We can see that the learned models can generate realistic textures, faces, and scene patterns. The texture images displayed in the left are modeled by a simple vanilla ConvNet EBM. The phase images shown in the middle are generated by an EBM trained via a cost-to-phi expanding and sampling strategy. The scene images in the right are sampled from the EBM learned by diffusion recovery likelihood. The energy-based model can also be useful for image inpainting, which is related to addressable memory. Once the model is trained on fully observed training examples, given a test image with a mask that occludes some pixels, we can run a few steps of Langevin Dynamics that is initialized with the occluded image to recover those missing pixels. From this figure, we can see that the model is very creative to inpaint diverse and reasonable patterns for each occluded image. The first row shows the masked images, and the last row shows the corresponding original images. Other rows show different inpainting results. In this example, the model is trained by a multi-stage cost-to-phi expanding and sampling strategy. It means that we gradually expand the resolution of the energy function so that the training and sampling can be more stable. As to unpair the image-to-image translation, people might recall the cycle gun, which trains two adversarial frameworks with a cycle consistency loss. Here, we want to show you how to use energy-based model without explicitly using the cycle consistency loss for this purpose. We can easily train one single energy-based model for one-sided image translation. Specifically, given two collections of images representing two different domains, the examples in these two datasets are unpaired. Therefore, this is an unsupervised image translation problem. What we need to do is to train an energy-based model on the target domain. However, during training, we need to initialize the short-run MCMC with some random examples from the source domain at each iteration. Once the training is done, the short-run MCMC will serve as a flow generator that maps the example from the source domain to the target domain. Since learning an EBM corresponds to matching the statistics of the translated images to the target images, the translated images not only maintain the contents of the original images, but also obtain the style from the target domain. Such an energy-based method is simple and natural because no explicit cycle consistency loss is needed. Now, let's move to the video domain. The spatial-temporal generative ConvNet is an energy-based generative framework defined on video. It generalized the generative ConvNet by using a bottom-up spatial-temporal ConvNet to parameterize the energy function, which is helpful to capture spatial-temporal information from videos. The model is in the form of exponential tilting of a Gaussian reference distribution and trained by analysis by synthesis. Langevin Dynamics is used to draw samples from the distribution. I will show that later. Different designs of the function f in the model can represent different types of video patterns. Dynamic textures or texture motions exhibit statistical stationarity in a temporal dimension. Examples include flowing water. Spatial temporal filters that are convolutional in both spatial and temporal domains can be used to design the energy network F. Here, we have some synthesis examples generated by the energy-based model that use 3 layers of spatial temporal convolutions with rule nonlinearity and subsampling operations. For each example, The first one shows the observed video, and the rest two are generated by Langevin sampling from the model. Many dynamic textures have structural background and objects that are not stationary in the spatial domain. For example, a video exhibiting burning fire hitting a pot. In this case, we need to modify the network F used in the last case by using filters that are fully connective in the spatial domain at the second layer to account for spatial non-homogeneity of the dynamic textures. Qualitative results are displayed in this figure. The energy-based spatial-temporal generative ConvNet can learn from videos with occluded pixels. This task corresponds to unsupervised video in painting or recovery. Since in the training stage, the model doesn't have fully observed training data, the learning algorithm of the energy-based model for complete data can be adapted to this application with minimal modification. The modification is that for each iteration, we run a few steps of Langevin dynamics to recover the occluded regions of the training example. The additional Langevin dynamics for recovery is initialized by the observed occluded example, and it only synthesizes the occluded regions while keeping the visible paths unchanged. At each iteration, we use the recovered observed example and the synthesized examples to compute the gradient of the log likelihood and update the model parameters. The algorithm simultaneously accomplishes three tasks. The first one is recover the training data. The second one is synthesize new video examples. And the third one is learn the model parameters. Here are some recovery results by learning energy-based spatial-temporal generative ConvNet from incomplete data. There are three types of masks for occlusion: salt and pepper masks, mixing frames, and single region masks. Here, I want to emphasize that the model we show is different from denoising autoencoder. In denoising autoencoder, the training data are fully observed, and noises are added as a matter of regularization. It also differs from supervised denoising or supervised inpainting, where the prime model has already been learned from fully observed data. Also, learning from incomplete data can be difficult for GAN and VAE. Now let's talk about an interesting application of this learning while recovery algorithm. If a moving object in the video is occluded in each frame, it turns out that the recovery algorithm will become an algorithm for background in painting of video, where the goal is to remove the undesired moving object from the video. Here, we saw two examples of background in painting by energy-based generative models. Now let's talk about the application on 3D computer vision. We will first focus on energy-based models on 3D voxels. Energy-based generative voxel net is an energy-based framework for 3D volumetric shape representation. It parameterizes the energy function by a bottom-up 3D convolutional neural network and follows the same modeling and learning scheme of the generative ConvNet. This model is powerful for 3D volumetric shape generation and outperforms GAN-based and VAE-based methods in terms of inception score, which is a measure to quantify the synthesis quality. To generate high-resolution 3D shapes, the model can be trained more efficiently by multi-grid modeling and sampling strategy. We can learn a pyramid of energy-based generative voxel nets. Each of them accounts for one resolution. Each scale of model is trained against the training example at its corresponding resolution. The pyramid of training examples at different resolutions can be obtained by downsampling the original example. The benefits of the multi-grid modeling is that during training, the low-resolution EBM can provide initialization for the MCMC of the high-resolution EBM. Usually, sampling from low-resolution space is much easier than sampling from high-resolution space. The starting minimal resolution is typically 1 by 1 by 1, and the largest resolution is the target resolution. Here are some results of generating 3D volumetric shapes by multi-grid modeling and sampling. The target resolution is 128 by 128 by 128. Sim-size example at each grid is obtained by 20 steps of long-range sampling, initialized from the sim-size examples at the previous cursor grid, starting from the 1 by 1 by 1 grid. Different scales of sim-size along the multi-grid sampling process are also displayed. "3D shape recovery" is another interesting application of the generative voxel net. Given a corrupted 3D shape with known voxel positions of the corruption, the goal is to recover the corrupted voxel. Here, I'm going to introduce a self-supervised method to achieve this goal. Given a data set of 3D shapes, we can easily generate a corrupted versions of dataset by randomly masking some voxels of each 3D shape. Then we learn a distribution of invisible voxels conditioned on visible voxels. Such a conditional distribution can be used for inpainting. The model is trained by analysis by sim-size scheme, where the sampling from the conditional distribution is achieved by starting from the corrupted example and then run a few steps of Langevin dynamics to obtain a sim-size example. We fix those visible parts and only update the corrupted regions. The recovered examples are used to compute the gradient of the log likelihood to update the model parameters. Here are some results of 3D shape recovery. For each category, the first row shows the original examples, and the second row shows the corrupted testing examples. The last row shows the recovered result by the learned model. The recovery is performed by running a few steps of Langevin sampling, starting from the corrupted examples. Similar strategy can also be applied to 3D super resolution, which seeks to increase the resolution of a testing 3D object. A low-resolution 3D dataset can be easily created by downsampling a higher resolution dataset. Then a distribution of high-resolution 3D shape conditioned on the corresponding low-resolution 3D shape is trained for super resolution. The idea is similar to the one in the recovery application, except that the sampling from the conditional distributions are different. For sampling, it first upscales the low-resolution example by expanding each voxel into a d by d by d blocks. Here d is the scaling ratio of constant intensity to obtain an upscale version of the low-resolution example. And then it runs Langevin dynamics starting from the upscale versions to obtain the high-resolution output. Super resolution results for category toilet, and sofa are shown in the figure. The energy-based generative voxel net can be useful for classification. We need to first train a single model from all categories in an analysis by synthesis manner. The learned bottom-up network can be treated as a feature extractor. We can learn a multinomial logistic regression classifier from the labeled data based on the extracted feature vectors for classification. The table on your right-hand side shows a comparison among different baselines for 3D shape classification. Point cloud is another important data format to represent 3D objects. It is a standard 3D acquisition format used by devices like LiDAR on autonomous vehicles, Kinect for Xbox, and face identification sensor on phone. Compared with voxel representation, point clouds can provide a compact and detailed representations of a 3D object. Learning a generative model of 3D point clouds for point cloud generation, reconstruction, and classification is a fundamental problem for 3D computer vision. A major challenge in modeling 3D point cloud is that, unlike images, videos, and volumetric shapes, point clouds are not regular structures, but unordered point sets, which makes extending existing energy-based paradigm intended for structured data not straightforward. Energy-based generative point net is an energy-based model for unordered point clouds, with the energy function parameterized by a well-designed input permutation invariant bottom-up network. The MLE training of the model follows analysis by synthesis scheme. The input permutation invariant bottom-up network F first takes all unordered points as input, encodes each point into features by multi-layer perceptron MLP, and then aggregates all point features to a global feature by average pooling, and eventually output a scalar by another MLP. This figure shows some 3D point cloud synthesis generated by the learned energy-based model by short-run MCMC. Since the model is trained with k-step short-run and non-convergent MCMC, the sampled point cloud X is highly dependent to its initialization Z. Therefore, the short-run MCMC process can be regarded as a k-layer flow-based generator or a latent variable model with the initial point Z as the continuous latent variable. We can use this latent variable model for reconstruction purpose. To be specific, given a new testing point cloud, we find the latent Z of the short-run MCMC generator to minimize the reconstruction error. The figure shows the performance of reconstruction. The second row displays the result of the energy-based generative point net. The third row displays a baseline point flow. Since the short-run MCMC is a latent variable model, we can also perform interpolation in the latent space to demonstrate that the learned latent space is meaningful. Here are some examples. The transition in each row displays the sequence of reconstruction with the linear interpolated latent variable Z. The learned point encoder in the score function can be useful for point cloud feature extraction, and the features can be applied to supervised learning. We first train a single generative point net on the training examples from all categories. We then replace the average pooling by a max pooling layer in the learned score function, and use the output of the max pooling as point cloud features. Such a point cloud feature extractor is also input permutation invariant. An SVM classifier can be trained from label data based on the extracted features for classification. The table shows the classification accuracy using the 1 versus all rule. The 3 curves show some robustness test, considering 3 types of data corruptions. Type 1 is missing points, where we randomly delete points from each point cloud. Type 2 is added points, where we add actual points that are uniformly distributed into each point cloud. Type 3 is point perturbation, where we perturb each point of each point cloud by adding a Gaussian noise. We report classification accuracy of the classifier on the corrupted version of point cloud data. The performance decreases as the corruption level increases. In the case of missing point corruption, even though 94% points are deleted in each example, the classifier can still perform with an accuracy 90.20%. In the extreme case, where we only keep 20 points in each point cloud, the accuracy becomes 53.19%. In this section, we will talk about energy-based continuous inverse optimal control and trajectory prediction. The problem of continuous inverse optimal control is to learn the unknown cost function from expert demonstration. This problem can be studied in the framework of energy-based model, where the observed expert trajectories are assumed to be random samples from the probability density function, which is defined as the exponential of the negative cost function up to a normalizing constant. In particular, we talk about the control problem of finite time horizon, where the trajectory is over a finite period of time. We will focus on the problem of autonomous driving as a concrete example. Let xt be the state at time t. The state might include longitude, latitude, speed, heading angle, acceleration, steering angle. Let's use ut be the continuous control or action at time t. The control might include the change of acceleration, change of steering angle. The dynamics f is known. We use both t and both u to represent time sequences of state and control respectively. The trajectory is the pair of both x, u. The cost function with learnable parameter is defined on the trajectory and some history and environment conditions. The problem of the inverse optimal control is to learn the parameters of the cost function from expert demonstration D. The distribution of control conditioned on the history and the environment can be represented by an energy-based model, with the cost function serving as the energy function. States X can be determined by the control U according to the dynamic function. As to the demonstration, control U are assumed to be sampled from the distribution, so that U tends to have low cost. The parameters of the cost function are learned by maximum likelihood by analysis by synthesis scheme. For the synthesis step, the trajectory of X and U can be sampled by long-train dynamics or predicted by optimization methods that directly minimize the cost function. Once the cost function is learned, trajectory prediction can be performed by Langevin sampling from the conditional distribution. Here are some example results of the trajectory prediction. The red dot represents the ground truth trajectory, and the green dot and the blue dot represent the result obtained by energy-based framework and GALE, which is GAN-based baseline. The energy-based framework can be generalized to the multi-agent scenario, where there are k agents, and each agent has a trajectory. In this case, we simultaneously control all vehicles in the scene. The overall cost function is said to be sum of each agent. The prediction is still performed by Langevin sampling from the learned energy-based model. In this section, we will move to energy-based framework for internal learning. Different from external learning, where the goal is to learn a distribution of a dataset, the internal learning seeks to learn a distribution of patches within a single natural image rather than relying on external data. The patch-wise Generative ConvNet is an energy-based framework for internal learning. It trains a pyramid of EBMs and trained against a pyramid images of different scales. Each EBM is trained by analysis by synthesis and is responsible to generate images based on the patch distribution learned from the images at the corresponding scale. A cost-to-find sequential training and sampling strategy is used to train the model efficiently. Specifically, the sampling process starts from a randomly initialized noise image with the minimum scale. For each scale, the initial synthesis is updated by k steps of Langevin revision, except that the initial synthesis at the minimum scale is from uniform distribution. The Langevin dynamics of any other scale is initialized from the upsample version of the Langevin output at its previous scale. The left figure displays some results of unconditioned image generation. Each row demonstrates a single training example and multiple synthesis results of various aspect ratios. The framework is able to generate realistic images with arbitrary size and aspect ratios by sampling from the learned distribution that capture different scales of internal statistical properties of patches within the input image. The right figure shows the influence of the numbers of scales that we use in the model. Given a single image, can we learn to increase its resolution without relying on external data? The patch-wise Generative ConvNet can perform this task. We first learn a model on this single image. After the pyramid of EBMs is learned, only the largest scale of EBM will be used to increase the resolution of the original image. The resolution of the original image can be increased by multiple times of expansion. Each expansion includes an upsampling operation and MCMC revision by the largest scale of EBM. This figure shows some example results of single image super resolution. Given a background image, we can manipulate it by either copying and moving some region, or pasting an external object in it. The parameterized generative ConvNet can blend the pasted object with the original background image, or smooth the artifacts due to editing. We first train the model on this background image and obtain a pyramid of EBMs. We then create the downsample version of the edited image. We then use the pyramid of the learned EBMs to perform the multi-scale sequential sampling, starting from the downsampled version of the edited image. The multi-scale MCMC revision can smooth the artifact of the edited image by minimizing the energy function at different scales. Here are some examples. The top example shows that the model can blend the original image with an external object by preserving the object's identity and applying the learned texture and color information to the object. The left example shows that if the edited image is a painting that specifies the layout of semantic object, then the resulting synthesis will be an image in which the global structure of the painting is preserved, while the texture matching the background image. The right example shows that the method can remove the artifact of the edited image where some region of the image is edited. Now let's start to talk about another type of energy-based framework, the generative cooperative network. The energy-based generative cooperative network have been very successful in unconditioned image, video, and 3D shape generation. Now we focus on supervised conditional learning by generative cooperative network. Just a little bit notation. Let X be the D-dimensional output signal of the target domain, and C be the input signal of the source domain. C defines the problem, and X is the solution. The goal of the conditional learning is to learn a conditional distribution P of X given C, which is the distribution of the target signal given the source signal, or the distribution of solution given the problem. Examples of conditional learning include label-to-image synthesis, image-to-image synthesis, and supervised image in painting. The unconditioned cooperative learning scheme can be easily extended to the conditional learning problem by jointly training a conditional energy-based model and a conditional generator model. Both two conditional models represent the problem and solution from two different perspectives. The conditional energy-based model learns an objective function in the form of a conditional energy function, so that the output can be generated by optimizing the objective function, or more rigorously, by sampling from the conditional energy-based model. This corresponds to slow thinking, because the sampling is accomplished by an iterative algorithm, such as Langevin Dynamics. The conditional generator generates the output directly by a nonlinear transformation of the input and the noise vector, where the noise vector accounts for uncertainty. This amounts to fast thinking, because the conditional generation is accomplished by direct mapping. The two conditional models are trained jointly in a cooperative manner, where the conditional generator serves to initialize the sampling process of the conditional energy-based model, while the conditional energy-based model refines the initial solution by an iterative algorithm. We call the conditional generator the fast-thinking initializer, and a conditional energy-based model, the slow-thinking solver. The solver learns from the difference between the refined solution and the observed solution, while the initializer learns from the difference between the initial solution and the refined solution. Here are some examples of image generation conditioned on class label. The figure on your right-hand side displays the top-down level that we used for the conditional generator and the bottom-up level that we used for the energy function. Here are some examples for supervised image-to-image generation by the Learn Generative Cooperative Network. In this section, we will talk about unsupervised image-to-image translation. Unsupervised cross-domain translation is more applicable than supervised cross-domain translation because supervised image-to-image translation relies on paired training examples between two domains. However, manually pairing up examples between two domains is costly in both time and efforts, and in some cases, it is even impossible. For example, learning to translate a photo to Van Gogh style painting requires plenty of real scene photo paired with their corresponding paintings for training. Now, we will introduce an energy-based framework which is the cycle-consistent cooperative network for unsupervised image-to-image translation. Suppose we have two image collections from domains X and Y, respectively. The examples of these two sets are unpaired. The cycle-consistent cooperative network simultaneously learned and aligned two cooperative networks. Each contains an EBM and a generator for one direction of translation. We take the direction from Y to X as an example. The generator G from Y to X, parameterized by an encoder-decoder, maps example from source domain Y to the target domain X. While the energy-based model P of X further refines the mapped result by Langevin Dynamics, such that the revised results match to the examples in the target domain in terms of statistical properties. The other pair accounts for the other direction of translation. Two directions of mapping are aligned by enforcing mutual invertibility on the two generators. Now, we are going to talk about the learning algorithm of cycle-consistent cooperative network. The algorithm is called alternating MCMC teaching, which iterates the following three steps. First, cross-domain mapping. Secondly, density shifting. Third, mapping shifting with cycle consistency. In step 1, which is cross-domain mapping, for each domain, we randomly sample some training images and use the generator, which is an encoder-decoder structure, to map them to the other domain. The output of the generator is revised by a few steps of MCMC of the EBM in the other domain. This means that those translated examples will be sent to the local modes of the EBMs. The generators are visualized as arrows in this figure, with red color indicating a mapping from domain Y to X, and blue color indicating a mapping from domain X to Y. We will use X and Y to represent training data, X hat and Y hat to represent outputs by the generators, and X tilde and Y tilde to represent the outputs of the MCMC by the EBMs. In step 2, given the refined sequences X tilde and Y tilde and the observed data, the EBMs can update their parameters, which is equivalent to shifting the EBM density toward the data distribution. Step 3 is about how to update the translator or generator G. Each translator G is trained with MCMC teaching laws, which means they shift their mapping to the EBMs. We also align these two mappings by enforcing gy to x and gx to y to be inverse functions of each other. This amounts to adding a cycle consistency loss in practice. Here are some results of unpaired image-to-image translation by the cycle-consistent generative cooperative level. Results shown on your left-hand side are style transfer from photorealistic image to artistic style. The result displayed on your right-hand side are season transfer between summer and winter. Next, I'm going to talk about unsupervised sequence-to-sequence translation. We can generalize the cycle-consistent cooperative level to learning a translator between two domains of sequences, where paired examples are unavailable. For example, given an image sequence of Donald Trump's speech, we can translate it to an image sequence of Obama, where the appearance of Donald Trump is transferred to Obama, but the speech is in Donald Trump's style. In order to adapt the original cycle-consistent cooperative level to image sequence translation, we learn an actual recurrent model in each domain to predict future image frame given the past image frames in a sequence. We use Rx and Ry to denote recurrent models for domain X and Y respectively. Each recurrent model is trained to minimize the output reconstruction error. With the recurrent models, we modify the cycle consistency loss of the generator G to take into account spatial-temporal information, and we call that the spatial-temporal cycle consistency loss. The final loss for training generator G and the recurrent model R is a sum of the recurrent loss, the spatial-temporal cycle consistency loss, as well as the MCMC teaching loss. Here, we show some qualitative results of unsupervised sequence-to-sequence translation. In the first example, we translate Obama's facial motion to Donald Trump. In the second example, we translate the blooming of a violet flower to a zero flower. In the third one, we translate the blooming of a purple flower to a red one. Now, we will show how to learn a generative cooperative level for saliency prediction. Saliency prediction aims at highlighting salient object regions in images, which is a binary image segmentation. For example, given an RGB image, we output a binary saliency map to indicate the salient object. Such a task has a wide range of computer vision applications. Existing salient object detection methods mainly focus on supervised learning, which relies on label data, and most existing supervised learning methods seek to learn a deterministic mapping between image and saliency map. Different from deterministic methods, Generative saliency prediction methods aim at learning a distribution of saliency y given an image x, and performs saliency prediction via sampling y from the learned distribution p of y given x. Now, we will represent this distribution by a generative conditional cooperative network. The cooperative saliency prediction framework consists of an energy-based model serving as a fine but slow predictor, and a latent variable model serving as a coarse but fast predictor. The energy-based model and the latent variable model are jointly trained by cooperative learning algorithm via MCMC teaching. Once the model is learned, the cooperative prediction is performed by a cost-to-phi sampling. That is, given an input image, the energy-based model and the latent variable model cooperate with each other to output the results. Let X be an image and Y be a saliency map. The energy-based model can define an explicit conditional distribution of the saliency map Y given the image X. The energy function is defined on both X and Y, which maps both X and Y to a scalar. This energy function can be regarded as a trainable cost function of the task of saliency prediction, while the prediction process by Langevin Dynamics can be considered as finding Y to minimize the cost U of Y and X given an input X. Such a framework can learn reliable and generalizable cost function for saliency prediction. However, due to the iterative sampling process, EBM is a slow but fine saliency predictor. On the other hand, the latent variable model defines an implicit conditional distribution of saliency Y given an image X. The saliency prediction can be achieved by an ancestral sampling by first sampling a Gaussian Y noise Z and then transforming the noise and the image X to the saliency map Y. Since the ancestral sampling is a direct mapping, which is faster than the iterative Langevin dynamics. However, without a cost function as in EBM, the learned mapping is hard to generalize to a new domain. The cooperative saliency prediction framework combines these two predictors and predicts the saliency of an image by a cooperative sampling strategy, where it first used the cost saliency predictor to generate an initial prediction by a non-iterative ancestral sampling, and then use the phi saliency predictor to refine the initial prediction via iterative Langevin revisions to obtain the revised saliency map. This framework offers the best of both worlds. As to the training, at each iteration, for each input image, the algorithm first generates a saliency prediction by ancestral Langevin sampling, and then use the generative prediction to update the EBM and the latent variable model, respectively. This is a standard learning process of the conditional ConvNet, where the input image is the condition and the saliency map is the output. Here are some prediction results generated by the learned model. Given an input image, the saliency map is stochastic, and we can use a sample average as the final prediction. This table shows a comparison of performance among different baselines and the cooperative learning framework. You can check the paper for the experimental details. The cooperative Saliency Prediction framework can be learned from a partially observed training dataset, where only partial pixel-wise annotation is available, for example, scribble annotations. This is a weakly supervised saliency prediction setting. The previous algorithm can be easily adapted to this scenario. For each iteration, we only need to add 2 steps for recovering the scribble annotation y. One is a recovery step by the latent variable model. It infers latent variables of the scribble data and then recover the missing region by mapping the inferred latent variables back to the saliency domain. The other is a recovery step by the energy-based model. It runs a few steps of MCMC starting from the initially recovered results provided by the latent variable model. The model update steps are the same as before. These are the recovery results and the prediction results. The algorithm can recover the missing annotations while training, and the trained model can output reasonable stochastic saliency maps. Now, we will talk about applications of latent space energy-based models. We will first briefly go over the model. The latent EBM is a top-down generator with an energy-based model as a prior. The energy-based model is standing on a top-down generator model. This informative EBM prior is a collection of the non-informative Gaussian prior. The EBM built on top of the generator can capture rules or constraints in the latent space. Also, sampling in the latent space is much easier than that in the data space. In order to model text, the generator model can be a conditional autoregressive model, which is parameterized by a recurrent network. And Z is a fault vector about the whole sentence and follows an energy-based prior model. Each xt is a token. The table shows a performance comparison among different methods in terms of forward perplexity, FPPL, reverse perplexity, RPPL, and negative log likelihood. The FPPL measures the fluency of the synthesis sentence. RPPL measures the distributional coverage of a learned model. The negative log likelihood measures the reconstruction of the model. The latent space EBM prime model shows competitive performance against other baselines. Now, we will talk about molecule generation by latent space energy-based model. Molecule generation is a sequence generation. We still use an autoregressive model as the generator and build an EBM prime on top of the generator. The EBM prime can capture chemical rules implicitly in the latent space. The figure shows some synthesis examples. The synthesized molecules are evaluated in terms of validity, novelty, and uniqueness. The table shows a performance comparisons of the EBM prime models against some baselines. Now let's talk about anomaly detection. If the generator and EBM prime are well learned, then the posterior P of Z given X would form a discriminative latent space that has separated probability densities for normal and anomalous data. Take samples from the posterior of the learned model and use the anomalized log posterior as the decision function to detect anomalies. The table shows a performance comparison. Now we will talk about saliency prediction using generative transformer with an energy-based pry. Traditional saliency prediction methods are typically supervised or semi-supervised because they rely on labels or annotations. They are also deterministic because they learn a direct one-to-one mapping from image to salience map. A conventional framework for deep silent object detection involves two main modules. The first one is a convolutional encoder-decoder for salience map generation. The second one is a loss function to guide the encoder-decoder for parameter update. The goal of the above two modules is to achieve a mapping function from the input image space to the output saliency space. Two main issues exist in the conventional deep saliency frameworks. First, the sliding window-based convolutional operation makes the deep saliency model less effective in modeling the global contrast, which is essential for silent object detection. Secondly, the one-to-one deterministic mapping or regression mechanism makes the current framework impossible to estimate the pixel-wise confidence of model prediction. Also, deterministic method usually doesn't have stochastic property. It is hard to learn from incomplete data or cannot be used for unsupervised learning setting. To solve issue 1, we can use a vision transformer to replace the encoder-decoder structure. For example, Swin presents a hierarchical transformer with a shifted windowing scheme to achieve efficient transformer network with high-resolution images as input. Also, we can study generative modeling of the supervised saliency prediction problem by using a generative model framework. That is, we try to learn the probability distribution of saliency map given an input image. Instead of using a non-informative Gaussian pry, we try to model it as an EBM. Combine all this together, we will present a generative vision transformer with an energy-based pry model for saliency prediction. Let's talk about the modeling. This model is a latent variable model with Z representing low-dimensional latent variables. Let's use I to denote an image and S for a saliency map. For deterministic mapping, we just need to learn mapping from I to S. But for stochastic mapping, we want to model a distribution of P of X conditional on I. We need to add a noise or latent variable Z that follows a pry distribution for randomness. That is, we map I and Z to S by a transformer network T, whose parameters are theta. This will change the one-to-one mapping into a one-to-many mapping. For EBM prime model of Z, we parameterize the energy function by a trainable deep net U, whose parameters are alpha. We will jointly train the parameters of the transformer network theta and the EBM pry alpha by maximum likelihood estimation MLE without using extra inference network or adversarial discriminator. We can use beta to denote both theta and alpha. The likelihood is a conditional likelihood. The learning gradient of beta consists of two parts, both of which involve an intractable expectation term under the posterior distribution, P of Z, given S and I. The first part is about the learning of the parameters alpha of the EBM prime, and the other part is about the learning of parameters theta of the transformer. Now again, we use MCMC sampling to assess the intractable posterior distribution to approximate the expectation term. The update of the EBM prime still need an MCMC to sample from the EBM. We use Langevin Dynamics, which is initialized with a Gaussian noise distribution P0 for MCMC sampling. To draw samples from the energy-based prime model, P alpha of Z, we iterate the Langevin step shown in equation A, which seeks to find Z to minimize the energy function U of Z. To draw samples from the posterior P of Z, given S and I, we iterate the Langevin steps shown in equation B, which seeks to find Z to maximize the John density P of S, Z, given I, given the image and saliency map. The John density involves the parameters of both EBM prime and the transformer generator. We use Z plus and Z minus to denote respectively the samples from the posterior distribution and the prime distribution. The gradients of alpha and theta can be computed with S, I, Z plus, and Z minus. The parameters can be updated by using the ADAM optimizer. We present the full learning and sampling algorithm of the model in algorithm 1. Given an input image I, the saliency prediction is performed by sampling from the learned conditional distribution, which first sample a Z from the EBM prime and then use the transformer to map the Z and I into the saliency domain to get S. We can use the sample average as a final prediction. The model performs very well and obtains state-of-the-art performance against other methods. Here are some qualitative results. The first row shows input images, and the second row shows the ground truth. The third and fourth rows show results of the current state-of-the-art saliency model and the generative transformer with EBM prime. The rest of the applications will be presented by Dr. Wu.
Another important application is the trajectory prediction. Suppose we want to predict the trajectories for pedestrians, multiple pedestrians. And here again, we can use a latent Z as a thought vector or a belief vector for the whole trajectory. So it generates the whole trajectory. And then we can treat this prediction problem as a inverse planning problem. So that is, we instead of learning a autoregressive model, very much like a policy network, we actually learn the value for those agents, those pedestrians. So this is encoded by this f of alpha z. So that is the negative energy function defined on z. This is like a value or a cost, but it is defined on the whole trajectory through the latent belief vector. So this formulation, I think, is very important because it goes beyond the Markov decision process framework, which underlies the modern reinforcement learning, deep reinforcement learning applications. in the sense that this model, first, it doesn't assume a Markovian dynamics. In fact, it put a probability density of distribution over the whole trajectory. It treats the whole trajectory as a whole thing that will be generated without this dynamic Markovian structure. And also, the value function is not a simple summation for stepwise cost. So this, I think, is a very useful generalization over this MDP framework, and it performed very well in terms of trajectory prediction. And this model can also be used for semi-supervised learning. As I mentioned, energy-based model is a generative classifier, but this time we built the classifier in the latent space. So that is, we now have a label. This label is like a class label, a categorical or one-hot vector. And this Z is a dense vector, and X is observed example, say an image or a sentence. And this time we have a latent space, energy-based model that couples this symbolic one-hot vector and this continuous dense vector. And then again, this X is generated by Z. So that is, given Z, then Y is independent of X. So Z is like an information bottleneck. In fact, this top-down model actually gave us a better or more natural interpretation of information bottleneck. And then the prior distribution is again a energy-based model, but the energy is in the form of a coupling between symbolic one-hot Y and continuous dense Z vector. And then this conditional distribution of X given Z continue to be a generation model or a RM model for the text situation. And this P of alpha Y given Z is just a softmax classifier. So that is, we learn a classifier in the latent space, the regular softmax classifier in the latent space, where supposedly Z should extract all the information in X that is relevant to the classification, to the class label or category Y. And in fact, we can learn this model unsupervisedly. So that is, we don't need Y. We can sum out this Y, and we can continue to use this log likelihood to learn all those models. And we can also bring in the label data so that we can add the conditional log likelihood. So this is just cross-entropy loss for the classification. Okay, so by joint maximization, we can then learn from both label data and unlabeled data. And in fact, this method achieve quite impressive performance for semi-supervised learning on text data and tabular data. And also it performed reasonably well on the image data. And we can also use this as a similar model for the controlled text generation. So again, X is a sentence text, and Z is a latent thought vector. But this time we also couple this with Y. Y may be, say, different topics and different emotions, sentiments, or different actions. Okay, and then we still have such a model so that this is a latent space energy-based model, and energy is a coupling between Y, symbolic Y, categorical Y, and dense continuous vector Z. And we can also learn a inference model to amortize or approximate the short-run MCMC sampling from the posterior distribution within the variational autoencoder framework. Okay, so we have all those elements, and we can learn the model in an unsupervised way or in semi-supervised setting. More importantly, so this is the likelihood, the elbow, the evidence lower bound in the VE framework. We can also add this term so that we can decompose this regularized objective function in those three terms. So one is a reconstruction for learning this generation model, and the other is the prior learning for learning this prior model, P alpha, the latent space energy-based prior model. And this term is quite interesting. This actually defines the information bottleneck. So that is, by adding this term, we actually arrive at this information bottleneck in the sense that we want this Z to extract information from X, but only as far as it is relevant for predicting Y. So this is the information bottleneck. So that is, this quantity actually appears very naturally in this top-down model. And the top-down model is more natural for abstraction. So this Z is the abstraction of X for predicting this Y. And this model can be learned in unsupervised setting or supervised setting. So that, for example, in the unsupervised learning, we can actually discover the action and emotion labels in the daily dialogue, so that we can sample the actions and the corresponding sentences. For example, the action may be inform weather, or the action may be request the traffic, and then we can generate those utterance or sentences. And we can also generate the text in a very controlled way according to the sentiment. We can control the sentiment, and we can generate, say, positive or negative reviews using our model, because we have latent sort vector, which is generated by a energy-based model, and this sort vector controls the generation of the whole sentence. So I think now we arrive at the conclusion of this tutorial. Just as a summary, so in this tutorial, we present the following models and methods. So first, we present the data space EBM, the energy-based model in the data space, say in the image space or in the video space. And also, we studied the interaction of the EBM with the generative model. For example, we studied cooperative learning and the divergence triangle learning for the joint training for energy-based model and the generative model, where the generative model serves as a approximated sampler. And we also studied the latent space EBM, where we move the energy-based model to the latent space, which seemed to be an even more natural home for all those MCMC calculations. And in fact, for the text data, this is discrete data, but you can still move to the latent space so that it is a continuous space. You can still use Langevin Dynamics for sampling. And finally, why is energy-based model useful? Hopefully, from this tutorial, you get some basic ideas why they are useful. But just to summarize, so first, it can be a very good density estimator, and also it can be very strong a synthesizer. So it can generate very realistic images, especially because on top of the generator in the cooperative training, there's also a refinement process guided by a learned energy function or objective function. And you can think of this energy function captures the soft objective or cost or value, or capture the soft regularization or rules or constraints. So here by soft, I mean probabilistically. So it's not deterministic, it's probabilistically. And also, perhaps more importantly, you can think of this energy-based model as a generative classifier. And then you can actually learn it from unlabeled data as a matter of contrastive self-supervised learning. For example, in this flow contrastive estimation, right, we use a noise contrastive estimation framework. So it actually unifies both this discriminative learning and generative learning. Okay, so this concludes our tutorial. I hope that you find this tutorial useful and helpful, and hopefully I will see you guys produce more interesting work along those directions. Thank you very much.